Alright, so in this particular problem, we have an object of mass 4 kilogram that is initially at rest at x equal to 0. So the problem starts at the origin. It's just a variable force. Key phrase here, variable force is applied to it as the object moves in the x direction. And it says the graph below shows the subsequent behavior of the variable force with the position of the object. Alright, here's part A, B, and C, and D. Here's F versus X. Alright, let's crack it out. Part A wants us to find what is the net work done on the object between 0 to 8 meters. So if you look at the graph, 0 being at the origin, that's the starting point. And then it kind of slopes upward towards 8, and then it goes flat from 8 to 12. So the first thing you got to realize is you're given an F versus X graph. So there is certain information you can pull out of this type of graphs. Here, the net work is simply the area beneath the graph. So all you have to do is make sure you shade correctly. If the area is above the x-axis, that's positive work or work done by. Alright, other than that, let's crack out part A. Part A is pretty easy. So to find the net work from 0 to 8, all I have to do is find the area. So watch my cursor from 0 to 8. That is a triangle. That's a right triangle. So all I have to do is find the area of the right triangle, which is this 1 half times base times height. Other than that, here's the shaded area. If you count correctly, the base is going to be 2, 4, 6, 8. And then the height is going to be 10, 20, and 30. So if we plug it in, it'll be 1 half times the base, which is 8, times the height, which is 30. And if you simplify it on your calculator, the area is 120. So the net work done is 120 joules. So key concept here, net work is the area beneath an F versus X graph. And that is it for part A. Now, if you wanted to, in case you're in a calculus-based class, if you wanted to, you can actually use calculus to do this. Net work is just the integral of f of x with respect to dx. Here, all I have to do is find this line. Okay, here is a diagonal that went 8 to the right and 30 up. So if you use y equals mx plus b, here, b is 0 because it intercepts at 0 because it starts at the origin. All we have to do is find the slope. The slope here being 30 divided by 8 because it's rise over run, rise being 30. The run being 8. Okay, so the slope of this line, if you punch in your calculator 30 divided by 8, you get 3.75 x. Here, once again, I left out b because b is the y-intercept and it intercepts the graph at 0. So here we have y is equal to 3.75 x, y being f of x, and f of x depends on x. So here I can substitute in what f of x is. F of x is simply 3.75 times x because it's constantly varying. Okay, so the problem says that it's a variable force. So here we have f of x as a function of x. Now, if you integrate f of x with respect to dx, that'll give you net work. So if you integrate this function, you get 3.75 x squared divided by 2. And then the bounds here are going to be from 0 to 8 because the question asks us from 0 to 8. All right, other than that, if you plug in the upper bound, which is 8, 3.75 divided by 2 times 8 squared, you'll get the same answer, which is 120 joules. I'm not going to worry about the lower bound because 0 squared is just 0. 0 times anything is just 0. So this one kind of makes it easy. All right, other than that, as you can see, you can just find the area. You can use calculus integrating the slope line there, which is give you the area, which is the same answer. All right, 120 joules and 120 joules. Let's move on to part B. Part B asks you to determine the object's instantaneous speed at 8. Here, it's just instantaneous speed. So really, all I have to do is find instantaneous velocity, but just leave out the direction because speed is a scalar. So what I want to do is I want to apply the work-kinetic energy theorem. Here, we already know the work from 0 to 8 is, 120 joules, because we just found it in part A. But I can break up net work equals the change in kinetic energy, which is Kf minus Ki. And then I can just cross Ki out because initially it starts at rest. The problem said so. Here, in order to find instantaneous speed, I'm going to have to break up Kf because Kf has speed in there. So here, Kf is just 1 half mvf squared. And then we can substitute values in. The 120 joules represents the net work done from 0 to 8 meters. And then 1 half gets carried down. Mass is 4 because it's given. And the final speed here is vf squared. So all I'm going to do is 1 half times 4, which is 2. And then to get vf squared by itself, I need to divide both sides by 2. So 120 divided by 2, which is just 60. So here, vf squared is equal to 60. And then to find vf by itself, you would square root 60. So therefore, this square root of 60 will give you about 7.75 meters per second. And because it asks for speed, I'm just going to give you that answer, 7.75 meters per second without the direction, because speed is a scalar. All right, so the answer to B is 7.75 meters per second. Here, it says, let's move on to part C, excuse me. Part C asks us to calculate the object's kinetic energy at 12 meters. So here in the graph, you notice it goes from 0 to 12 meters. I've already taken care of from 0 to 8. We already know that's 120 joules. So to find the object's kinetic energy at at 12 meters, all we have to do is apply the work-kinetic energy theorem again. Why? Because we know that net work is the change in kinetic energy, and I can break up delta Ke into Kf minus Ki. Here, once again, I can cancel out Ki. I'm going to start from 0 meters and go to 12 meters, okay? You could, if you want, actually start from 8 meters, but I'm just going to start at 0 meters. Why? Because the object's initially at rest, so I can just cancel Ki out, which makes, I think, my life easier. So therefore, net work is simply Kef. Well, to find net work, all you have to do is, once again, find the area correctly beneath the F versus X graph. So here, the first area we already found, which is 120 joules. The next area that I have to shade in is this rectangle. So here the rectangle is, the base is 4, because from 8 to 10 is 2, 10 to 12 is another 2, so that's 4. And then if you count the scaling correctly here, it's going to go all up to 30. So base being 4, height being 30. So if you do that correctly, you should get 120 joules, because 4 times 30 is 120. And then other than that, consensus sets, what is the kinetic energy from, at x equals to 12. I start at 0, I'm going to go to 12. So the net work would simply be both of these areas shaded together, because I start at 0, I'm going to go to 12. And that, the net work done here is 240. And then Kef, that is the answer. Okay, so Kef is the net work done. The net work done is just 120 plus 120, which is 240 joules. All right, let's do part D. Part D asks us to calculate the time required to travel from 8 to 12 meters. So here's 8, here's 12. Right away, I know that from 8 to 12, the force stays constant. It stays at a constant 30 Newton. If force is constant, acceleration is constant. If acceleration is constant, you can use your kinematics equations. So I'm just going to go ahead and do average acceleration is change in velocity over change in time. The question asks you to find time from 8 meters to 12 meters. So here, the I say for t, I'm just going to flip-flop t and a. So I'm going to move t up to the top left. I'm going to move a to the bottom right. I want to break up delta V into VF minus VI, because change is final minus initial. Other than that, I'm going to go ahead and substitute out VI. VI, we start at 8. So in the previous part, we found that the velocity, or the speed, excuse me, at 8 meters is 7.75 meters per second. So I'm going to take the final, can't speak right now. I want to take the final velocity. I'm going to subtract it from the initial velocity. So here, final velocity is unknown. The initial velocity starting at 8 meters is 7.75. I don't know what my acceleration is. So here I have highlighted VF and A. I have two things that I need to find. But this is pretty light work, okay? I can just apply Newton's second law from 8 to 12 meters, because force is a constant here. So therefore, net force in this case is just 30 newtons, because at 8 to 12 meters, the force is a constant 30 newtons. Mass is 4 kilograms, so I'm going to substitute that in. So to find A, I'm just going to take, I'm just going to divide both sides by 4. So 30 divided by 4 will give you 7.5 meters per second. So I just found A. Well, now I need VF, right? I have two things that I don't know. I just found A, so I need to go get VF. Well, to get VF, I can just say that the kinetic energy final is equal to 1/2 mvf squared. Well, here we go. VF here, okay? VF here is pretty light work. We already know what the kinetic energy is. We know that the net work done for the whole entire system here from 0 to 12 meters is 240 joules, which is Kef. Okay. Well, Kf here I replace with 240 joules. 1/2 gets carried down. M is 4 because it's given. Vf is my only term that I don't know. So therefore, if you take 1/2 times 4, which is 2, 240 divided by 2, which is 120, and then to find VF, you need to square root 120, which will give you 10.95. So I ran out of space here, but that's how you would do it. Once again, 1/2 times 4 is 2. To get VF squared by itself, you need to divide both sides by 2. 240 divided by 2 is 120. But then to get VF by itself, you need to take the square root of both sides. and the square root of 120 is about 10.95. Other than that, I just found VF. So for VF, I want to plug in 10.95 minus 7.75. That was the VI at 8 meters. And then the acceleration I calculated, which is 7.5. And then if you simplify all that on a calculator, you should get a time of about 0.43 seconds. Okay. Other than that, I hope that helps. Yay, I made it through the video without coughing. All right, stay nerdy, don't be whack.